Co audio jest też.
Mariusz, can we start? Możemy zacząć?
Yes, you can.
Tak? Możemy?
Yes, you can.
Yes, we can.
Oh, yes, we can. Okay. Good afternoon, everyone. We are hosting today our alumni, Zofia Kaczmarek. Zofia did her bachelor studies here at this observatory, and then she moved to Cambridge to graduate and carry out her master degree. And now she's a PhD candidate in Heidelberg at the University of Heidelberg, and she's working on microlensing and black holes, and that's the topic of her talk today. So yeah, so the floor is yours, Zofia.
Thank you very much, Milena, for this nice introduction, and welcome everyone. I would like to talk today about optimizing microlensing black hole yields, and I would like to give a huge shout out to the amazing microlensing team at the Lawrence Livermore National Laboratory and the University of California. These are my collaborators. I know Milena gave already a little bit of an introduction, but I will just visualize something I call my orbit here, and I do not yet know where this orbit leads afterwards and whether it's periodic or more chaotic, but I'm very happy to be back here at the university where I did my bachelor's, and I have many, many great memories with this place. And as Milena said already, I did my master's at the University of Cambridge. Here is the photo from my graduation. And now my PhD thesis in Heidelberg is focused mostly on microlensing in Gaia. We are preparing for the new data releases and time series data, and I have joined the DPAC consortium to help in this effort. But part of my PhD was a tiny little detour to the US for an internship at LNL in a program called the Data Science Summer Institute, and this will be the focus of my talk today. So I will first introduce this program in case any of you would like to apply, because I strongly, strongly encourage that. It was an amazing opportunity that really paid off as a learning opportunity and also for future collaborations. This is a program hosted by the Livermore Lab that invites 30 interns from all over the world to participate in this very intensive 12-week program. So 50% of the time is devoted to an individual research project, and 50% is a very intensive data science program, including lectures, hands-on exercises, and a final data science challenge. And as a leading laboratory in terms of computer clusters, world-class GPU, CPU clusters, it is a really great place to learn data science. So if you have any questions, especially for students, you can feel free to ask me about this afterwards. And my individual research project was called Hunting the Milky Way's Rogue Black Holes with Bayesian Statistics. And if I were to wrap this long title into something practical, I would say it's, in practice, building a classifier that tells us which lenses are best black hole candidates. And first, you must forgive me that I will give a background on microlensing as a quick reminder. You probably see this kind of slides quite often, but I would really like for this talk to be accessible across all fields. So what we are looking for is a chance alignment of the mass acting as a lens and as a light source, and this lens distorts the image of the source and causes this very characteristic blip in the light curve that we can look for. There are some problems, there are some challenges that we face in looking for this kind of events. So the first one is that it's very, very rare. So if you look at a single star, the probability of being lensed is the order of 1 in a million. So what we have to employ is specialized high cadence surveys that look at millions of stars. But also, we can only learn this much from a light curve, and we have a challenge that we call degeneracies, that different parameters, different combinations of physical parameters of the lens of the source can give light curves that look just the same. So we cannot really uniquely determine the physical parameters from the light alone. If we want to measure mass of the lens, we need to have some additional information from, for example, from measuring this tiny shift in position caused by lensing. Yeah, on the previous slide, I have shown a lightcurve from OGLE. You know OGLE very well. It's a great specialized microlensing survey. And we have many, many more surveys coming up in the future 2 years. So we have the LSST survey at the Rubin Observatory. We have the next data release of Gaia that will give us entirely new data products. And we have the Roman Space Telescope that will very deeply survey a tiny field in the Galactic Center, giving us both photometry and astrometry. So if you want to start doing microlensing, it's a very exciting time. And why do we do that? As I said, what we need is a mass that aligns with our light source. So this is a method that's sensitive to dark objects. And as such, it is the only known method so far with which we can detect isolated black holes. And the only one isolated black hole confirmed so far is called OGLE 2011 BLG, and here's the serial number. That was discovered by microlensing just 3 years ago. So again, exciting times. Why did we have to wait so long for the first black hole? Because it requires extremely, extremely, extremely high precision in astrometry. That's just on the border of what we can do with our technology currently. And the observing program for this lasted about a decade. So this is a very big challenge. And we would like to have not one isolated black hole, as I have just shown. We would like to have an entire population of black holes. And that is the motivation between us constructing the classifier. So why do we want to do it in this automatic statistical way? Well, first of all, let the sky speak for me. You can see that the sky is not static. We can have, every time we look at the sky, there are many, many things happening at once. And this video is made by Łukasz's team to visualize Gaia events, about 360 events found in Gaia science alerts all over the sky. So already it is pretty hard to track as a human to look on events, at events one by one. What we will have very soon with Roman, with Rubin, with all the upcoming surveys that I've shown, will be tens of thousands of microlensing events per year. So this stream will be just impossible to analyze for humans with visual inspection and dedicated modeling for each event. At the same time, while we have this huge, huge inflow of events, only a select few will be followed up in astrometry. Astrometric follow-up is still very expensive. You need time, for example, on the Hubble Space Telescope, on JWST. And you have to schedule it in advance. You have to convince that this is a science case that's worth it. And those telescopes are, of course, very oversubscribed. Even when we have Roman, I'll let it run in the background, even when we have Roman that will provide us astrometry straight away, most events, so most of the sky, will be covered only by photometric surveys, and most discoveries will still be made only with photometry. And that is very important, for example, if you do what I'm very interested in, so you want to do some statistical studies of the entire galaxy. You want to see where black holes are situated, where neutron stars are situated, if those are different distributions in the galaxy. So we will still need to choose our prized best candidates for astrometric follow-up. And finally, what I think is a very big encouragement for this kind of studies is that we have the recent discovery of OB 110462. So this is a great first step to start filling this stellar gray here, this kind of Mantary distribution, with events from microlensing. This plot has a high preference for events that have, for black holes, neutron stars that have a very specific evolutionary paths. A large majority are in binaries, a large majority are extragalactic. So we can answer really a lot of questions when we have galactic isolated black hole populations or isolated remnant populations. So is there a mass gap between neutron stars and black holes? What black hole masses are allowed? Is there a mass gap between stellar mass and supermassive black holes? Are the distributions of black holes in our galaxy the same as distributions of extragalactic black holes? And so on and so on. So really, it's a big stack of treasure that's waiting for us. And to maximize the yield of those treasure searches, we have published this paper on finding black holes in photometric microlensing surveys. That has been published just over a week ago. So you can look into it. It has been featured in some news like the data science newsletter of the lab, and also in Astrobytes, where it has a very depressing title. I am very hopeful that my talk will not be a lonely sob story, but more of an exciting outlook of future science. But I do appreciate the fun. So how does this classifier work? And of course, as very often, we will start from the Bayes theorem, and we will keep complicating things along the way. So what our target is the probability that our lens belongs to a given lens class. So, for example, black hole, given the data and given a galactic model for a class from some list of classes. And when we try to break the Bayes theorem into parts, we can see where we can get the different needed ingredients. So this highlighted in pink, we can get from a galactic simulation for event abundances. This factor is not dependent on class. If we just want relative probabilities, we can neglect it. And this part we can get from sampling from the event posterior. So we conduct some modeling like MCMC or nested sampling, and we have some approximation of a smooth distribution. What's very important is that when we classify a single event, we do not have to take into account the detection efficiency of a whole survey. And if you're interested in how that works in the statistical framework, you can have a look at Scott Perkins' paper from last year. Now I will stop torturing you formally, and I will go to the practical implementation. So what we are really doing is we have some modeling, for example, from nested sampling or MCMC. And here in this work, we have been using modeling of Nate Golovich and his group, also at LNL, who did a very, very detailed study of OGLE microlensing events, where they also include effects such as variability and the baseline. So those are the best parameters, the most precise parameters you can get. And for modeling, we get this little posterior distribution that's shaded in blue. And on the other hand, we have lens populations from galactic simulations. And for this, we have used the popsicle software, population synthesis model, which is the current state-of-the-art model for galactic simulations involving lensing and involving compact objects. So it was a very demanding challenge because it took about 20 node days per run. And we did several runs injecting different galactic model assumptions. So you can see that's a lot of CPU hours, and that is why LNL was one of the best places in the world to conduct this kind of research. So the candy-colored solid line distributions are from the galactic simulations. So what we want to do, said very simply, is we look at our posterior, we look how similar it is to all of the other distributions, and then we correct it for the priors that we applied along the way. And we can do it for any set of parameters, but we're choosing TE and pi-e for the simple reason that we can always get some constraints from the light curve on those parameters. So TE is very intuitive. It's just the event timescale, how long the event is. Pi-e is a little bit more tricky. It's an imprint of the Earth's orbital motion, so as the Earth moves around the sun, our line of sight changes slightly. So this perfect alignment is like a little bit wobbly. So if the event was long enough, we would see wiggles in the light curve with a period of a year. Usually events are a little bit shorter, so what we see is just asymmetry of the light curve. And that's how we can intuitively describe this axis. The more asymmetric the event is, the higher up. And to get a bit of intuition, I decided to visualize this with a little bit of exaggerated wiggles. And I also wanted to show it to you in sound, because I've been doubling in sonification. So this is how a short event would sound like. So this is an entire year condensed into 3 seconds. If you want to proceed to a longer event, so this is a long and symmetric event. And now I really hope you can hear the asymmetry in the light curve for this one. So we can hear the little wiggles. So I hope that was enough to get a bit of an intuition of the space we are working in. So now let's explore this space a little bit more. And by the way, this figure is from this recently published paper of mine, and all the figures from this point, unless indicated otherwise, will be from this paper. So if you wanted to go back to something, that's where you can find it. We decided to explore for a given point, if we know the TE pi parameters exactly, how confidently can we make a classification? And from that, you can see several things. First of all, you can see that for stars and for black holes, there exist some regions in which you can make a very confident classification that this should be a star, this should be a black hole. This is great because what is most exciting for us and what we want to look for most is black holes. In case of white dwarfs, we only have several blobs when we can make a confident classification. And in case of neutron stars, it is not possible at all, because those distributions are nested in the rings of a far, far more numerous stellar distribution. There are different methods to classify them. I will come to that later. But for now, let's be focused on black holes, and let's be happy that we can do it from photometry alone. Another thing you might have noticed is that we have this very weird black blob that doesn't really look like anything. This black blob was the focus of a very long part of work in the individual research project, and also a very important part now of the classifier itself. So let's stop and think about this blob that we call the non-class. So no classifier ever can be perfect. And we can divide reasons why our classifier is imperfect into 2 categories. So first of all, our classifier isn't perfect because our image of the galaxy isn't perfect. We don't know everything, and because of that, our simulation won't be perfect. So there might be some missing physics. And the easiest example of missing physics is there is some entirely different population that doesn't belong to any other class. So for example, we could have had primordial black holes that occupy some region in this space that is entirely not covered by simulation. But no matter how perfect our simulation and no matter how perfectly we know the physics, we have a finite number of events. So we will always have sampling effects. We have those tails here where we have just some single events. And those tails are very noisy. So we can have a noise from the sampling. We can have numerical effects for very small numbers. So in those parts, classifications will be very uncertain. And if we leave that in, if we don't consider the uncertainty, we'll have a very weird situation where the most confident classifications, the best white dwarf candidates, will be here, but there are no white dwarfs at all that look like that in the simulation. So to get rid of this kind of artifacts, we created the non-class. So this is a way for the classifier to rate its own uncertainty. So the higher the non-class probability, the more the classifier is saying, I have not seen any event like that in the simulation, so I cannot make a confident classification. And how we did it in practice is we created a top hat kernel for all the simulation samples, and we use a top hat because it's very good at making a sharp cut. So here we have a cut between the regions that we consider covered in the simulations and the regions that are terra incognita. And we can use this also to find the missing physics. So for example, if we had a lot of events classified as none, we can look into them again one by one. Another part of the classifier that I feel is worth noting is the moving part. So I hinted already that our models of the galaxy are different. It will try different assumptions. And what we focused on in this work is different ways of generating remnants. So we know assuming different physics of remnant generation significantly impacts what we see in microlensing. But also, we do not know yet which solution for physics of remnant generation is the correct one. So there are several simulations, several works existing in parallel in literature. And here we use three. So the Spera 2015 IFMR is one that is purely analytic. So we have a progenitor mass, we have a metallicity, and we know exactly what's going to turn out on the other side of the supernova. Then Reifel 2018 made some simulations of supernovae, and they concluded that it's not really like that. If we have very massive stars, sometimes they will explode and we can have black holes, but sometimes it can proceed a little bit differently and we will have neutron stars, and there is some randomness. So instead of just one line for a function of final mass as a function of initial mass, we will be splitting into two branches, and which branch our event will go to has some probability. And then there was a suite of simulations called 6 volts and 20. So that includes both the effect of this randomness and explosions, but also different metallicities, because the simulations I just mentioned were solar metallicity only. But it is not just a combination of the two, it is an entirely independent suite of simulations. And again, there is no one solution that we say is correct. We wanted to try all of them so that we can also see how that impacts our classifications. And we classified 10,000 events, and we can see that which model we choose has a very large impact on how many black holes we have. So here we made a classification of an object being a black hole if the probability of being a black hole is higher than any other class. And what the yields are is very, very variable. But we have decided that for our strong candidates, we'll choose those events that are classified as black holes regardless of what we inject into the model. So no matter what galactic model is used in construction of the classifier, it's always a black hole. So that's how we found those 23 new strong black hole candidates. And those light curves are from OGLE. I do not need to introduce the OGLE project here. It is an amazing survey that has been going on for decades, providing breakthroughs not only for microlensing, but other transients and variables. And we have this beautifully densely covered light curves from OGLE that allow for this very detailed modeling that I have mentioned. So we have OGLE 3 and OGLE 4 data. Those are events from 2002 to 2017. So we can't exactly do astrometric follow-up because those are long gone. We have tried to still play around with those events a bit. For example, we tried to predict what their astrometric signal would be like, which is the color in this plot. But if there is something that anyone would like to still do with this data set, we have made all classifications public, not just for the 23 black hole candidates, but for all 10,000 light curves and for all 3 IFMRs. So if you have any ideas to use it, you can let me know. I'd be very happy to see it used. And just as a curiosity, if we plot out all 10,000 events in here, we can see that from some moment, the probability of a lens being a black hole is almost a linear function of a position on the diagonal here. And if even this classifier, even though it's very fast, is too complex or too computationally expensive, this is a good first approximation for probability of a lens being a black hole. So I mentioned astrometric signal. We can make some predictions, but you remember at the very start I said that from photometry alone, not much can be said about the physical parameters. And we're very, very posterior dominated. So in black we have the prior dominated, sorry. In black we have the prior from the galactic simulation. So what we assume for black holes before seeing any data, and in magenta we have our 23 candidates. So usually the light curve doesn't help us narrow down the distribution much. But we can look into things like detectability. So currently with, for example, Gaia, with Hubble, we have around 1 milliarc second precision. And still, even if we have very good black hole candidates, follow-up is still a little bit risky because the probability for them to be detected is around 0.3, 0.4. But very soon with Roman, we will have 0.1 milliarc second astrometry, and pretty much all of our events will be easily detectable. So current instrumentation is at the very, very edge of detecting signal of black holes, stellar origin black holes. And again, this is a great time to get engaged in microlensing and astrometric microlensing. Of course, if we had astrometric signals, something I had to do was to look into detectability with Gaia. And this is how our perfect high theta E candidate looks like in Gaia, will look like in Gaia if it had data. So one tiny square in this grid, 1 milliarc second, is almost exactly the precision of Gaia at this brightness. And it would have beautiful data if it had not happened too early. So Gaia started observing in July 2014. That means that only the dark purple tail of this astrometric track could be covered. So what about other events? This event was too early, the others were mostly too faint. So Gaia astrometric precision is extremely dependent on magnitude. We have some promising indication in here that astrometric signal could be more or less like the precision, but we have no indications of any excess astrometric signal from RUVA, which is the unit rate error, which indicates there's something beyond the 5-parameter solution. All the others are too faint, but they are still worth revisiting when we have time series astrometry and not just fit results. So maybe there is still something hiding in one of those 4 events that overlap with the Gaia timeline. Finally, I'll just mention that our classifier does not exist in a vacuum, and there are different methods of trying to tell what the lens is. And one of them is dark lens code that's being developed by Łukasz's team. And we have compared our results to dark lens code. So we took our 23 lenses and we analyzed them through dark lens code. So for all of our lenses, the dark lens probability, so this is interpreted as we have a certain mass and distance distribution, and can it be explained by a star of this mass at this distance? Or is there just not enough light observed to fit a star in there? So the probability of the lens being dark is over 97% for all of our lenses. For most of them, it is 99.9%. So those are very high confidence dark lenses. And for all of them, the masses are between 13 and 91 solar masses. So if it's dark, if it's in this mass range, it has to be a black hole. So we agree on that. We don't exactly agree on the angular scales. And that is because our methods simply have different approaches for filling this missing information. So that's a recurring theme, the missing information that we don't have from photometry alone. Dark lens code uses dynamics, so we have to have some extra data on relative motion, on the source proper motions, and dark lens code is very dynamical. What we have is a simulated population, so we have some underlying expectations on mass. So this is entirely something expected, but what is encouraging is that we agree on those objects being black holes. And once we've looked into our black hole candidates quite a lot already, maybe we can go back to the very start, to the first only known isolated stellar origin black hole that has been motivating our endeavors. And what is very surprising is that our classifier says it's a white dwarf from photometry only. So now I have a very difficult task, because I have to say it doesn't mean that it's not a black hole. We know for sure from astrometric follow-up that it is a black hole. I am also not trying to say our classifier is rubbish, because if it was, I wouldn't be giving an entire talk saying that it is a new tool and you should be using that. So what happened is that follow-up of this object was simply a high-risk decision that gave an immense payoff. But following up this event and all the others that were followed up in this observing program was a high-risk decision, as you can see that they're all more consistent with this cyan white dwarf population than with the black hole population. And if one of them had to be a black hole, it makes sense that it would be this one, which is quite consistent with the outliers in here. So those decisions on follow-up were made around 14 years ago. So the landscape of microlensing was entirely different. Now we not only have galactic simulations that are more detailed and are customized for microlensing, we also simply have way more events to choose from. So what is going on now, what is happening right now with proposals being sent on Hubble Space Telescope JWST is there are searches that are focusing on this very space, so on high TE, low pi E events. So we can probe this population of black holes. And we can have a look at why our classifier said it was a white dwarf. Well, most probably a white dwarf. You can see the posteriors from modeling this event, and you can see that they fall into this extremely dense region in contours of relative probability. So this is just the plot of relative probabilities that you saw at the very beginning, but overlapped with white dwarfs and black holes. And here are 30, 50, 70% probability contours. So a very small movement in here changes the classification entirely. So that makes us ask a question: is this object an outlier from the astrophysical population of black holes? Or is it just that we expect black holes to be in this region, but they do not necessarily have to be? So this is something that's very important, is that we have to maintain a link between simulations and observations. So simulations help us make classifications, but when we have confirmed mass measurements, confirmed classifications, we should give feedback to simulations and strengthen our science from both sides. And to make it more possible and to make it more accessible to the community, we have created popclass. So this is a lightweight software package for Bayesian classification, and you can use it with any set of parameters in any science case. So what's supported, what we gave with simulation results, is microlensing, and that's a primary application. But for any case where you have some parameter spaces, you have some samples, some simulation samples with known values of those parameters, and they are labeled, and you want to classify things, you can use it. So it doesn't even have to be astronomy. This package is publicly available, it is actively developed, and it is open for contributions from anyone. So if you would like to add your galactic model or add your a model for your specific fields in the galaxy or your specific survey, you are very welcome to. We'll be very happy to welcome those contributions. This package has been submitted to Journal of Open Source Software, and we are now after the first round of review. So when you open GitHub and look for popclass, you see this very nice animation of a drifting posterior and how probabilities change when we move in this space, but also when we make more observations and narrow down our posterior. So what do we have going on for the future? As I said already, we are going to continue development of popclass. We also want to integrate this classifier into target and observation managers. Here in Warsaw, you probably know Black Hole Tom. That is one such tool for managing which events are the most pressing, the most high priority, the most interesting to follow up. But other surveys also have those tools, and we would like to have a panel in the Tom software where when you open a target and observation manager, you can see a little visualization of where your event lies in the parameter space and what it is most likely to be. And then we could make classifications more or less in real time. The last thing that I would like to mention is I have shown this plot and said that neutron stars are very, very, very hard to classify from photometry alone. This classifier, as I said, can be applied to any sets of parameters. So if we go further into astrometry and make the same plot, but looking at time scales and angular scales of microlensing events, the situation changes completely. Now, neutron stars have one of the most saturated shapes in here, and we can really, really make high confidence classifications. So this is one of the things we'll have with Roman Space Telescope. What is very interesting is that this shape, how it looks like, where it's centered, changes very significantly depending on what assumptions we make in our galactic model. So this is very much a case where new observations will be able to inform our galactic models and make us choose the ones that are really a good reflection of our galaxy. So just a few messages to take home. We have created a new Bayesian classifier for microlensing events, and it is capable of identifying candidates for black holes. This classifier is lightweight, it is very fast, it is flexible because you can use it for anything. You can inject your own simulation. It doesn't have any rigid assumptions how the galaxy looks like. And it is ideal to apply as an initial filter. So we have tens of thousands of events that are impossible to process. We narrow it down to tens of events, and we can look into them in detail. And as a proof of concept, we applied it to archival OGLE events. We find 23 new strong black hole candidates. And in the future, we can keep finding candidates that are for events that are ongoing. We can help optimize astrometric follow-up efforts, optimize black hole yields, and also verify what we know about the galaxy. So, thank you very, very much for your attention. I am leaving some links if you would like to look into this more. And if you have any ideas for collaboration or contributing, feel free to contact me at my email. Thank you very much, and I'm happy to take any questions.
Thank you. Thank you. Thanks. Great job. Any questions or comments? Maybe Martin?
What percent of OGLE lightcurves has measurable Earth parallax?
So as I said, parallax is something we can constrain from the light curve, but not always it is not consistent with zero. In most cases, it is really consistent with zero, and we have some range of. So maybe I will get a little bit back. Sorry about this. I will get a little bit back to where we present the idea of the classifier. Yeah. So timescales are something we can usually narrow down pretty well. for parallax, we usually have just orders of magnitude. And yeah, and it's often consistent with 0, and it is not limiting the classifier, so we can work with just upper limits. And in fact, for black holes, it is enough to have upper limits.
So the most is upper limits.
So we have some distribution of possible parallax, possible PI values, but it is very often consistent with 0 because those are very, very subtle effects that are hard to constrain. So if we were to choose events that have parallax, or for example, from parallax we can measure the direction of relative motion, that would be a very small subsample. But if we want to see events where we can make a classification from this entire shape that is very extended in this direction, that's an application where it's not a problem that the constraints of parallax are not this strong. I hope this answers the question.
So I have a question about this population. I mean, I understand that you had to assume something about the population of solitary black holes in the galaxy. So what was the mass spectrum that you assumed, and how was it justified? And another question is that I noticed that most of these expected distributions are cut at the logarithm of TE of 2.5. Is this like a feature of the model that you didn't model anything longer, or it's like a prediction that with your models you will not see anything beyond 300 days? Okay,
so first of all, we did not make any cuts on masses that are allowed. The distributions come from Galaxia that generates progenitors. And then what is the distribution of black hole masses? That depends on the used IFMR. For example, the Reichfeld 2018 IFMR has typically lower masses. The other ones allow higher masses that result from explosions of low metallicity stars. But there are no artificial cuts. This is just what happens with this progenitor and this IFMR applied. And the IFMRs can be found in literature for this. Spera 15 is just Spera et al. 2015 and so on. As for 2.5, this is also not a sharp cut. This is consistent with the highest masses that the IFMRs generate. So in this case, in this plot, this is the Zuckervolt N20 IFMR, and I think it cannot generate, it will not generate black holes more massive than around 180 solar masses. But this is not anything rigid. This is just resulting from the progenitors and metallicities we get from Galaxia. It's just. It tails off. There is just not enough stars to have like any samples in there.
And does this black hole mass distribution have a gap, a high mass gap due to very expensive supernova, like above 60 solar masses?
Good question. I think it gets shallower, but does not have a gap explicitly, so it does not have any. If you plot a histogram, there is no, there are no events that have 0 events, but it does drop significantly. But I would have to look again, and
I think that the mass spectrum of black holes is a big question mark. So I think this is one of the biggest uncertainties in this classifier. But you have to assume something.
Yeah, this is also why we assumed a few different models, and we only make strong classifications. We only say it's a strong candidate if it agrees across all of the IFMRs, but of course they are all approximations.
Yes. So, actually, a couple of related questions. To follow Marcin's first one is the presence of the parallax, of the events. So So all the 10,000 events, they had a measurable parallax. This I find difficult to believe.
Yeah, that's so there is an MCMC modeling that gives you a posterior distribution of parallax. So typically they are very low, but what you can say is a range or orders of magnitude of parallax. You typically do not have a measured parallax in a sense. It's an exact value.
Parallax, you still use the constraint mass, which is
Yes, and it is it does not hurt our case because if we only have an upper limit, black holes have very low parallaxes. So we can still exclude the regions above here, and how deep we can go in the Y dimension will still be classified as a black hole. That does not impact if it's classified as a black hole until at some point, if we measure, like if we could very confidently measure that like exclude any parallax signal at a very low level, that would start falling into the non-class, but the distributions are wide enough for it not to happen.
Then, so these simulations, they apply to the bulge region, right?
Yes. So there are...
They look different in different parts of the galaxy.
Exactly, yes. So there are 20 fields, and they do not cover the entire OGLE footprint because they are very computationally expensive. So it would not be feasible, for example, to run the whole sky or the entire galactic plane. But they are specifically designed to mimic OGLE and to cover more or less uniformly the OGLE fields. And we welcome contributions, so we are happy to have people's simulations of their own surveys, and also we will probably add more simulations for more surveys in the future.
And last question, so you mentioned for the future you'd like to add it to the top.
Yes.
However, I assume your model is based on the full light curve. So have you tested your code? How does it behave if you cut the light curve in half?
Well, it's definitely...
The first half of the light.
So if you cut the light curve in half, it will be very hard to make classifications because parallax is very badly constrained. Parallax is constrained by asymmetry of the light curve. But what you can do is start making classifications and making requests for follow-up when you're a little bit after the peak, because while we have a... Maybe I'll go. That was a bad decision to make it not clickable. While at T0 we have a single peak for the photometric signal, the astrometric signal lasts for a much longer time, and also it peaks out at two symmetric points in the wings here. So if we are after the peak, we can still have a full, a full track that's enough to measure mass from astrometry. So that would be the window of opportunity to trigger follow-up while astrometric deviation is still high, but we have gone over the peak.
Okay, I don't see any more questions. There is also no questions on Zoom. So if any of you would like to talk to Zofia, she's around just after the seminar. We are also going for dinner. So thank you, Zofia.
Thank you very much
for your presentation. Next week, Joachim Borowicz from our observatory is going to tell us about his research on flaps based on OGLE data, and the reminder about the notebook, and also the reminder if any of you would like to help contributing into the public event on partial solar eclipse that is on the 29th of March, please let us know. Right? So, thank you.